Hi, so I wanted to prove something that hasn't appeared on YouTube, which I think is really cool, which is called the pumping lemma for linear languages. So a linear grammar is just a normal context-free grammar, except we have a restriction where we have exactly either 0 or 1 variables on the right-hand side of any rule. So any context-free grammar can have whatever you want on the right-hand side, but a linear grammar is where you have either 1 or 0 on the right-hand side. So just as an example, if we talk about the favorite non-regular language 0 to the n, 1 to the n, where n is at least 0, then the standard grammar for it is either s makes empty or 0s1. And clearly this rule right here, it has 0 variables on the right hand side, and this one has exactly 1. So this is a linear grammar by definition. So therefore this is a linear language by definition. So a linear language is just the same idea as a context-free language, except for when there's only a linear grammar. So one thing that you can pretty easily show is that the set of regular languages are a strict subset of the linear languages, which and what we're going to show today is that they are a strict subset of the context-free languages. So this fact right here is because every regular grammar has either 0 or 1 variables on the right-hand side already. And the fact that it's a strict subset comes from this guy, where we have a linear grammar, and so this is a linear language, but this language is not regular by the pumping lemma for regular languages. But I want to prove something for linear languages here. So let's think about a linear language. So let's let G be a linear grammar. So we know that all of the rules in the grammar are going to be something like A goes to U, B, X, let's just say. And where the U part and the X part are only terminals. So they're just a string of terminals. They could be empty. But they may or may not be empty. But they're only terminals, and there's exactly 1 variable on the right-hand side or 0 variables on the right-hand side. So let's think about a derivation. So if we look at the parse tree, so let's make a parse tree for a particular string. Let's call the string W, and let's call it W1 up to Wn. Well, the start variable at the very top, let's call it S. Well, it must make some part of the string, some terminal, followed by a variable, or a set of terminals, I should say, and followed by a variable, possibly, and then a set of terminals over here. And one thing that we're going to assume here is that this linear grammar has no A to B rules. And by that I mean there's no variable that's being replaced by another one. And we can assume that there isn't this without loss of generality, because if this is the case, then we can copy and paste the rules around so that, and then eliminate this rule entirely. So this is part of the conversion into Chomsky normal form, and we can do that without loss of generality. We can copy and paste rules around, and that won't change whether or not the rules originally were linear. So if we have a start variable going to some terminals possibly, may or may not, and then a variable, and then some terminal, then what the tree is eventually going to look like is kind of like a Christmas tree. So it's going to do some kind of fan out like this. And then it may hit the bottom somewhere. So what we should notice is that the nodes in the center are all variables. So all of these are variables. Okay, so let's see. So what we want to do in order to get some kind of repetition, to get some kind of pumping lemma type result, is we want the variables to repeat. So we know that if we make this tree tall enough, then eventually one of these orange variables is going to repeat. And actually S could appear over here, but you can actually assume that S doesn't appear on the right-hand side of any rule. But that's not really so important here. So we want some variable to repeat. Well, we want to grow this tree to be tall, so that means that if we read the leaves of this tree left to right, and it doesn't really look left, but this is the leftmost node of the tree, then if we read them in this particular order, so I guess going down on the left side, over and up on the right side, then we want to make that so long, so the string that we're trying to generate, so that we're forced to have the tree become taller. So if we, for example, let k be the longest right-hand side of any rule, and let's let n be the number of variables in G, maybe after removing those unit rules that I talked about earlier, then if we look at some string, let's look at some string w such that the length of w is, what would be good here? So it would be k, no, it's the other way around. It's n plus 1, so that we are forced to get a repetition, times k. So if the length of w is actually at least that number, then that means that if we do the absolute worst thing, which is to have every variable appear once, then that's still not long enough to generate this string. So if this string has this particular length or bigger, and we're able to make a parse tree for it, then a variable must repeat. So one thing that we need to be sure of is that w is in the language of the grammar to start with, so that there is a parse tree for it, and that fact right there, then at least one variable repeats, which is pretty nice. So let's think about what would it mean for a variable to repeat. So let's try to draw that parse tree yet again. So we got the start variable up here, we got some kind of Christmas tree thing going on, and then let's say some variable a appears right here, and then maybe further down the same variable appears yet again, and then some stuff happens down there. Okay, so let's try to figure out what happens here. Well, we notice that whatever this thing makes, so let's focus on this. So the a thing makes something like this. So that means that from this point down all the way through, a makes from this point this set of terminals. So from the point where I'm looking at right here, down and over to the right-hand side right here, that's what this a makes. So what we know is that a is going to make, in some number of rules, let's call it some string of terminals u, and then something I'll get to in a second, and then some set of terminals y. So I'm noting here that the u part and the y part are terminals. And then now let's focus on the second part of this right here. So this a down here is going to make only terminals eventually, or a different set of terminals, I should say. So let's give that a particular name. So this a, maybe I'll use a different color. So let's let it be purple. So this part of the tree is going to be made by the purple occurrence of a. And let's call that part w, just for convenience. Actually, I'm going to call it x, because I used w above. But now let's look at s. So if we make s yellow, so what we notice is that s is going to make some set of terminals right here, and then whatever comes after in the middle, which is going to be some variable, and then the right-hand side is going to be some set of terminals. So the s thing is going to make some set of terminals. Actually, let's give these different names. Let's give this to be v, and the s one is going to be u, and then something in the middle, z. So what we notice is that if we group these terminals, I'm going to call them initially u, even though I'm going to modify it in a second. So the s thing can make some set of terminals followed by some stuff I'm going to get to, followed by some set of terminals. And same thing for the first A, and the second A is going to be just some set of terminals. Okay, well, what I'm going to do here is I'm going to circle this part right here, and I'm going to call that thing U. And why am I going to call that U? I want to call that U because I want to stick the variable A right here. So the terminals that appear before the first occurrence of A on the left side, I'm going to call U. So that now I can put into the middle here the variable A. So I'm going to call that part U. And then for the V right here, I'm going to do something very, very similar. So I'm going to call, oops, I did not mean to highlight there. I'm going to call those terminals on the left side, I'm going to call those V, so that now in the center I can put the variable A. Okay, and on the right side I'm going to do something very similar. So these terminals I'm going to call Z, and I'll stick to the colors. So, and then these ones over here I'm going to call Y. And then this bottom bit here, those I'm going to call X. Okay, so if I read from the left side to the right side, I have U, V, X, Y, and then Z. Okay, so we have this relation between the S, the making U, A, Z. So that means that I can apply this set of rules any number of times I want. So that implies that S can make U, V to the I, X, Y to the I, Z for all I at least 0. So this is exactly the same condition that appears in the pumping lemma for context-free languages, which is not surprising because I can just copy and paste parse trees around. Okay, so what can we do here? So what we should notice here is that if there are so how many variables do we have? We had n variables. So that means that this path from the top to the bottom, so let's actually note this. So this length right here, I know it's a little crowded, but so that length is at most n, right? So therefore, let's see. So that means that the number of terminals right here is going to be, so let's think about this. So that means that the terminals that are involved before we get to this second occurrence of A are going to be the U variable, the V, the Z, and the Y. So that implies that the length of U, V, Y, and Z, no X in the middle, is going to be at most n times the, let's see, so that would be, it's actually at most n plus 1 because we're including the second occurrence of A. So it's going to be at most n plus 1 times the length of each right side, which is k, and that's what we set to be the length of the string that we gave it, the string that we're trying to generate here. So that's the length of W. Even though it could be at least that, we were going to set it to be equal at just for here. So that means that the first two pieces and the last two pieces combined together are not very long. And that's actually all that we need. So let's go ahead and state the pumping lemma for linear languages. So this is the, not R, pumping lemma for linear languages. So let's let L be a linear language. Then this is going to be very similar to other pumping lemmas. So then there exists a pumping constant. Let's call it P to mirror the other ones, for L, such that for all, for every single string in L with the length of W being at least P, So remember, this p was the number which was n plus 1 times k from before. So for every string that's in the language, which means that we can make a parse tree for it with the length at least a certain number, then that means that the variable repeats. Then what can we do? So then there exists a decomposition of w into u, v, x, y, and z, such that we have only several conditions. So we have 3 conditions. So the first condition is that the length of everything but the middle piece is at most p. The second condition I'll return to. And the third condition is u, v to the I, x, y to the I, z is in L for all I at least 0. So the pumping lemma for context-free languages here would have said the length of vy is at least 1. So do we get something similar here? And actually we do. So because, where did I put it? So we assumed that the grammar had no unit rules, then that means that the thing that appears on the left and the right of each variable can't both simultaneously be empty, because we eliminated them here. And that actually turns out to be crucial in some of the proofs using the pumping lemma for linear languages. So here, we're going to have vy having length at least 1. So this is, the last 2 conditions are identical to the context-free pumping lemma. This one is the one that's different, that makes it different. Okay, so let's go ahead and do an example of showing some language that's context-free, but not linear. So I'm going to have a language here, let's call it L, which is going to be a to the I, b to the I, c to the j, d to the j, such that I and j are at least 0. And I claim that this is context-free but not linear. So it's pretty easy to see that this is context-free because the I and j variables have absolutely nothing to do with each other. So we can make a variable that makes this piece, a variable that makes this piece, and then have a start variable that goes to whatever start variable for this, concatenated with the start variable for this. And that doesn't immediately prove that it's not linear, but that particular grammar is not linear because it's concatenating 2 variables there. So let's go ahead and show that L is not linear. And I just sketched that it is context-free. Okay, so it's not linear. So let's try to prove that. So let's let P be the pumping constant. Pumping constant for L. Then I'm going to pick a particular string. So I'm going to choose W to be A to the P, B to the P, C to the P, D to the P. And that very clearly is in the language because I and J are both P. There's no condition on whether I and J have to be equal or not. They just happen to be in this case. Okay, so let's think about what the decompositions look like. So the decompositions. So the important thing to realize here is that the length of u, v, x, y, not x, y, it's y, z. So the first 2 pieces and the last 2 pieces are at most p here. So that means that the first 2 pieces occupy at most p characters, and the last 2 occupy at most p characters. So remember, so let's try to blow the string up a bit. So we got a bunch of A's at the beginning, a bunch of B's, same number of them, some number of C's, and some number of D's. So that means that there are PA's, PB's, PC's, PD's. So the U part is the beginning of the string, so it must belong in the A part. And the V part is immediately appearing after the U, so that means that it also must be in the A's because there are PA's, And all 4 pieces together are at most p characters. Never mind that it's just the first 2. So that means that the u and the v part are in here somewhere. And that also means that the y and the z portion are way over here in the d section. So what was... And because the z part is at the very end of the string, and the y part is immediately preceding it, and together, all 4 pieces are at most p characters, and there are p ds at the very end. So, and crucially, we don't even care about the u and the z part because they're not really being pumped. It's the v and the y part that matter. So what I'm going to do here is let's choose I equal to 2. Then that means whatever the number of v's, the number of a's that v is, and the number of d's that y is, whatever happens, so u v squared x y squared z, because we got to pump the v and the y part in the same number, the number we chose. Well, that's going to be, we're increasing the number of a's by some number, so the a's goes up. So how many we had? We had p plus, let's call it k. And then we never touch the b's, we never touch the c's, and we increase the d's by some number. Let's call it L. It's not really important what it is. But we know that since v and y both can't be empty simultaneously, one of k and L is at least 1. So 1 of k and L is at least 1. So whichever one it is, either the a's and b's don't have the same number, or the c's and d's do not have the same number. So either number of a's is not equal to the number of b's, or number of b's, or a number of c's is not equal to the number of d's. Okay, and so that proves that this string cannot possibly be in the language. And so therefore, by the pumping lemma, L is not linear. So it's a very standard proof by pumping lemma technique. It's just using the pumping lemma in a slightly different way because we're using a different pumping lemma here. So hopefully that was interesting in that you were able to see something that you haven't before. Leave comments down below about the pumping lemma for linear languages. If you have any questions, I'm happy to answer them. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.